I'm Daniel Jackson Archer from Liberty University. I'm presenting a little bit of my undergraduate research on spiking neural network controlled artificial heart, advised by Dr. Wayne Strasser. Basically, just to give a brief introduction, when I was younger, my dad didn't like to turn up the heat in the house because it used more energy, so he would tell me just put on a sweater. So going kind of from that mindset, we can look at this a little bit in terms of energy consumption. As we get more and more technology in our world today, we consume more and more energy, as we've heard from all of the speakers talking about how data centers consume lots of energy. And if we need more energy, then we need more energy production. And as we get better technology and our technology advances, again, we need more energy. And as we get larger computational devices, we need more computational power. And as we get more computational power, in order to create that, we in the past have relied on Moore's law to double the number of transistors on a chip over a period of time. I think it's somewhere between 3 and 5 years. But as we know, Moore's law currently is slowing down because we're reaching the physical limit of how many transistors we can fit in a single space without interferences due to just the physics of the matter itself. So when we look at computers, most of the computers today that we use have something called a von Neumann architecture, which combines a processor with memory in a space in order to have the processor and the memory transfer information from memory to the processor, perform computations, and then with the computation, we get the result that we want. The problem with this, though, is that transferring information from the processor to memory costs energy. And so the question then is, if we have our computer and we have our processor and memory, how do we eliminate the loss of energy or the use of extra energy to transfer information from the memory to the processor? There's a very simple solution to this, but it's more difficult to implement just because it's not an architecture that we're used to. Essentially, we need to take the processor and put the memory in the processor, have them combined so that we're not wasting energy transferring information from the memory to the processor. This results in a more low power solution, which we can call a spiking neural network. Now, why is it called a spiking neural network? Well, first of all, it's biologically inspired. So a lot like other neural networks that you've heard of, neural networks are biologically inspired. This takes this to the next level. It is composed of nodes and directed edges that are not necessarily layered or dense and can be recurrent. Essentially, we have neurons and synapses, where each node is a neuron and each edge is a synapse. And we have from one neuron to another neuron connected by a synapse, another neuron to another neuron connected by a synapse, but then these two neurons may be connected by another synapse as well. Neurons, we can think of them a bit like buckets for potential. They will build up potential as potential is brought to them by synapses, and when they reach a threshold, they will spike across the synapses that are directed away from them. This gives us information transfer in time, as the neurons will build up potential over time, accumulated from other neurons spiking into them. But it also gives us information storage in time because they're holding on to the charge to release it later as more information is brought to them. Synapses have a weight which modifies the spike that is, or the amount of potential that a spike carries that is carried across them. So say if a neuron spiked with a value of 1 and a synapse had a weight of 0.5, then we could say that the amount of potential transferred from the presynaptic neuron, the first neuron, to the second neuron, the one receiving the spike, the postsynaptic neuron, would be 1 times 0.5. the potential times the weight, and the second neuron would receive a total amount of potential of 0.5, filling up its potential bucket by 0.5 potential. And if it were to receive 0.5 potential, which would put it over its threshold, say if it was at 0.8 potential, it received 0.5 potential, and if its threshold was 1, it would be at a total of 1.2 potential, and then it would spike, resetting its potential to 0 and sending a spike across its synapses directed away from it to the neurons that are connected to it with other synapses. Synapses also delay spikes. So they take the information, or they take a spike from a presynaptic neuron and then delay the time that it arrives at the postsynaptic neuron. So in order to illustrate this just a little bit, I've created a small spiking neural network. We can assume in this case that each neuron has a threshold of 1, and each synapse has a delay of 1 and a weight of 1. We're going to spike in some spikes into this neuron up here, in one of our 3 input neurons, and then later we'll see this, but we will track the times that the spikes come out from these 2 red neurons, the output neurons. The yellow is a spike. A yellow neuron is a neuron spiking, and a yellow synapse is a spike traveling across a synapse. So it looks kind of like this. So as we can see, one spike traveled through this synapse, or traveled from this neuron out through these 2 neurons. And part of the information storage that I'm talking about, you can see down here, where there's a loop where neurons will spike into each other and then continue to trigger this neuron off and on every once in a while, giving us another way of information storage in time. So the question then becomes, how do we get information into a spiking neural network, and how do we take information out of a spiking neural network after it performs its computation, which is what the spiking process looked like there. Basically, if we have a sensor, we can take either digital or analog data from our sensor, put it into an encoder that will then translate that information into a series of spikes over time. So maybe something like this for these 2 values. Basically, there's many different encoders, and I can go over them later if you would like me to, but this is the basics for how we translate information into the language that the spiking neural network will understand. Similarly, we need to take the spike train, put it into the spiking neural network, the spikes will propagate, and then we get an output spike train, something like this. Then we take that spike train and we reverse the process, put it into a decoder, and we get out a value. That value is our action value, and then we can use it to say, turn the leg of a robot. In this case, we're not turning the leg of a robot. What are we actually trying to do? We're trying to do artificial heart control. So artificial hearts are, of course, based on kind of a biological system, and total artificial hearts have a pump and a controller. They're battery powered, and they need to be frequently recharged. This is a power issue. Artificial hearts are typically either powered in one of 2 ways. They will be powered by a cord that goes from the artificial heart out of your skin to a battery that you will carry around with you, or they can be charged by wearing a vest via induction. And if you, say, are without your induction vest for half an hour, your heart runs out of energy, and unfortunately your heart stops working, which is not necessarily a great situation to be in. So if we could reduce the amount of energy that the controller needs in order to power the heart, then we could theoretically extend the lifetime where someone could be without their induction vest if they were in an unfortunate situation. We are aiming to use blood pressures to feed into our controller as our inputs to control the pump speed. In this case, we're using a relatively simplistic model, and we're going to combine it with a spiking neural network as the controller. So for the pump model, basically we're going to use a dimensionless angular velocity of a rotary pump, omega, where omega is just the minimum omega plus the range that omega can be times a value u, where u is the predicted value from 0 to 1 of the spiking neural network. The pump's volumetric flow rate, QP, is defined by this equation, which is a pump equation that I'm sure y'all recognize, but with A, which is a constant, and B, another constant, modifying this omega squared minus the change in pressure of the arterial and venous pressures in millimeters of mercury. And of course, QP can't be below 0. We always need it to be greater than 0 because we need blood flowing through our heart, if that makes sense. So the model that we're using for the heart is the Wynn-Kessel model, which we have the QS, the systematic blood flow, which is defined by the difference in pressure between the arterial and venous pressure, defined by R, the vascular resistance in the system, which is your circulatory system. And then of course we have to have our conservation of mass, where CA and CV are the compliance of the circulatory system in the arterial and venous ones specifically. So for observations, we're passing in the arterial pressure and the venous pressure, along with the mean arterial pressure target that we wish to achieve and the cardiac output target in liters per minute that we wish to achieve, which is typically between 3 and 8 liters per minute for regular activity. The action that we're getting is between 0 and 1, which is just normalized because it's easier for a network to output something between 0 and 1 instead of something like 88,000 or 8,000 RPM, if that makes sense. So this is the function that we've used to define the reward. Basically, this is the mean arterial pressure, the error in the squared error in the mean arterial pressure, the squared error in the cardiac output, and then 3 different penalties for safety, the smoothness of the motor control, basically saying that the rotation of the pump can't be going between like 100% and 20% of its maximum value, and then the suction penalty, which is a physical problem where the pressure difference is the pressure difference is not great for the heart itself. So before we go to results, some final notes. I've implemented a step decrease in the cardiac output target so that we're not just trying to approximate a straight line all the time, which simulates a change in activity level. Say you're running, then you start sitting. Do I have a couple more minutes, or should I?
Sure, you can go ahead. We have 5 minutes.
Okay. And this is just for dynamic control in various situations, and hopefully making this a little bit more robust. So preliminary results show with the red being the cardiac output target and the blue being the cardiac output that the spiking neural network predicted, that first of all, it's not exactly matching, which is great. Or not great. It's low, which ideally is not what we want, but we can see that right here, where the step decrease happens, if we look closely at that, we can see that the cardiac output actually reacts to it and goes down, which for a preliminary result is good. It means that the network is reacting to the step decrease. This is just the mean arterial pressure that goes along with the cardiac output. The mean arterial pressure behaves a little bit differently, but we can see that the mean arterial pressure here spikes when the cardiac output drops, which is not necessarily expected behavior, but it is expected that it would change when the pressure drops in some way. So this is a different network that trained on the same data set. As we can see here, this decreases about the time that this happens. That's a problem because if we look closely, we can see that the decrease starts before the drop does. And this means that we're overfitting to the target cardiac output. Again, this is the mean arterial pressure with the predicted and unpredicted. So basically, we're getting a cardiac output as a reaction to the target cardiac output decrease in some cases, but in other cases, we're overfitting. The mean arterial pressure is generally stable, but it tends to fluctuate at the cardiac output drop. So in order to reduce the probability of networks overfitting, we need to improve the randomization of the target drop time and the target behavior to make our networks more robust to different types of activity levels. And again, we had an overall trouble reaching the target cardiac output, which we can try and remedy by either training networks for longer, since these are preliminary results, or B, by adjusting our constants A and B. So next steps, we want to add sinusoidal and target cardiac output targets, implement a rate decoder to allow a better U range. Currently, we're using a winner-take-all decoder, which just puts us at the minimum and maximum speeds, which was an oversight on my part initially. And then we want to do a literature review to find suitable A and B values and randomize the time of the step drops to stop overfitting. These are my acknowledgements. Dr. Strasser, of course, of the University, and 10 Lab at the University of Tennessee, Knoxville, and Aaron Young at Oak Ridge National Lab. Thank you all for listening to my presentation.